Well, good afternoon or evening, everybody. Let's see, day 2 of transformations. I hope day 1 went all right and you understood the reflections and translations and what to do with points and lines and shapes. Um, day 2 is not really that complicated. It's just a little bit different type of transformation. Dilation, and this is a note you want to make. Dilation is the only the only transformation where all parts are not congruent. Okay, let's look at these two figures. What do you notice about the two figures? Well, obviously they're both triangles and they're both pointing the same way. However, if we had a measure here of 60 degrees, this triangle also would have a measure of 60 degrees, and this angle would have a measure of 70. Well, this triangle's angle that corresponds with that one is also 70 degrees. So we have 70, 70, 60, and 60. That's 130. This angle would be 50. And as you can see, all angles in each triangle stay the same. So really the only thing that gets preserved or stays the same, like grandmother's jelly, is angles. So the only thing that stays the same in a dilation are angles. Okay, a dilation occurs when a figure gets bigger or smaller by a constant. And a constant is a number that doesn't change, it stays constant. Okay, bigger would be like times 2 or times 3 or times 4. Smaller would be in like times 1/2 or times 1/4. So bigger is by a whole number, smaller is multiplied by a fraction. So let's look at what dilations do. So when you perform a dilation, the big D stands for dilation. The 2 is the constant, and the point, or whatever you're dilating, is the thing you're dilating. So 2, 4 is the thing you're dilating. So there's no shape here but a point. It's not that the point gets bigger, it's that the numbers in the point get bigger by times 2. So let's write, so 2, 4, so times 2, both of them, times 2. And we have a new point of 4 comma 8. All right, well, let's graph 2, 4. 2, 4 is, we'll call it A. And then 4 comma 2, 4, 6, 8. 4, 8 is a dilation that produces an image of A. So it is interesting because a dilation grows from the origin. You could almost put a ruler here and see that you could take, it's like a slope. You could go right up it, up 4 over 2 and up 4 over 2. So dilation grows the same amount away from the origin or towards it if it's a constant of a fraction. Okay, so let's try this one. So let's look at this problem here. It's a little bit different. We know it's a dilation, but we don't know the constant, but we do know this point dilates from here to there. So what happens? So 2, 1. How does 2 get to 6? It's, remember, only multiplication. So how does 2 get to 6? 2 times what equals 6? 2 times 3. So it should be a dilation of 3. Let's see if that's true for the y value. 1 times 3. So it's a dilation of 3. 2, 1, and 6, 3. So 6, 3. And if we put a ruler on it again, we can see that it does grow away. Times 3, up 2 over 1, up 2 over 1, up 2 over 1. Three slopes of 2 over 1. Let's look at what happens with these figures right here. Oh, we got our first constant of a half, so we know that this dilation is going to make this point grow smaller or towards the origin. Let's see how that works. Okay. So dilation of a half, so times a half, 4 times a half is 2, and half of $3 is $1.50. Okay, so our point, our original point is 4, 3, 2, 3, 4, comma 3. We'll call that A again. And our dilated point of 2, comma 1.5. And we'll call that A prime. You know what's interesting about a dilation of a half is you could see that dilation of a half is basically taking the point A and cutting the distance in half to the origin. So it's halfway to the origin. Okay, let's look at this next one. We're actually going to dilate this shape. This is a tough one because you know this point right here is going to be like way up here. We'll figure it out, no big deal. The regions will always give you a grid big enough. You just might have to move the x and y axis where you see fit. Okay, so let's go ahead and find the points of A, B, C. So this is A, this is B, and this is C. So A is 2, 2. B is 4, 2. And C is 2, 3, 4, 5, 6, 2, 6. So all these numbers are going to be multiplied times a constant of 2. So A prime is 4, 4 times 2. B prime is 8, 4. And C prime, whoops, is 4, 12. Okay. All right, so this is going to be tricky to graph, especially the 12, but we'll do what we can. A prime, 4, 4, so 4, comma 4. Here's A prime. B prime is 8, so 8, 1, 2, 3, 4, 5, 6, 7, 8. Well, 1, 2, 3, 4, 5, 6, 7, 8. And then 8, 4, so it goes up to like right here. That's B prime. A prime and B prime, and then C prime is 412. So 412 is like 4, 5, 6, 7, 8, 8, 9, 10, 11, 12. It's way up here, something like that. We'll do the best we can, no worries. And put our point. There we go. Whoops. And we have our figure, C prime. You can see that this figure multiplied times 2. I wonder what the area did. So a dilation of 2 gives me an area that's obviously bigger. What's the area of this triangle? 2, which is the base, times 4, which is the height. 2 times 4 is 8. 8 divided by 2 is 4. So the area of this is 4. 1, 2, 3, 4. So that's 4. 1, 2, 3, 4, 5, 6, 7, 8. So 4 times 8 is 32. 32 divided by 2 is 16. Ooh, so a dilation of 2 really takes this number and quadruples it. 4 times 4 is 16. That's interesting. Okay, well, what we're going to do is we're going to skip this one over here. And what I would like you to do is try this one right here. It's an interesting one. It's -2, so if it's on one side of the origin, it's probably going to flop to the other side of the origin. Okay, be careful of that one. So I want you to try this classwork. So try, and then under dilation with respect to the origin, the image, this becomes this. What is the constant? So graph it and figure out what the constant is. How do you get from -15 to -5? What do you multiply by? Okay, so try this one too. Great, we'll see you guys tomorrow.